Good day, and welcome to Africa Teen Gig. This is the STEM Digital School. I hope that everybody is good and ready to do some physical sciences grade 12 today. Yes, this is the grade 12 physical sciences. If you have just joined in, you have just come in at the right time. This class does start at 9 o'clock, and today we're going to be doing mechanics unit 3. We're going to be doing the chapter summary. For the past 5 days or so, yes, 4 days, we were working through this chapter of mechanics where we did work, energy, and power. So I hope that everybody was following through everything that we were doing and you now understand better and you're ready to do revision for this chapter as a whole. My name is Nonkululeko Matondo, and this is your grade 12 physical sciences class. I am your grade 12 physical sciences teacher. So I hope that you are ready to do some chapter summary. Okay. Another thing that I wanted to mention is that from here, I will usually work through the Siyavula textbook. I usually work through the study and master textbook. So if you have any of those or any other CAPS approved textbook, you are in the right place. Just go to the mechanics unit 3, the water, the work energy and power chapter, and we can work through that. And if you are struggling to get some of the textbooks that you need, you can go and get them. You can download the application that's called Snaplify. Snaplify is an application where you can get all the textbooks that you need absolutely free until the end of December, which is the 31st of December 2020. This was due to the COVID-19 problems where they have made, a special way they just giving people textbooks for free. And you can even view them offline. I view them offline. You don't need to have bundles for you to open any textbook. So you can get yourself some simplified textbooks and get your work going, okay? So going back to our homework, yesterday I did give you homework. I asked you guys to do number 2, number 4, and number 6 on the power problems because yesterday we were doing power and we did a couple of examples, we did a couple of problems. So I asked you guys to do the examples, number 2, number 4, and number 6. This is problems, and I hope that you guys managed to do them. For number 2, it says 2 students, Bill and Bob, are in the weightlifting room of their local gym. Bill lifts 50 kg barbell over his head 10 times in 1 minute, while Bob lifts 50 kg of barbell over his head 10 times in 10 seconds. What who does the most work? Who delivers the most power? Explain your answer. But you guys see, remember when we talk about work, for work to be done, there has to be a displacement. So if there's no displacement, I don't think there's going to be work. And if there's no work, there is no power. Okay? But let's just see how we manage to do it. So it says 2 students. Yes. So you see, the displacement is 0. So there is no work done. Since power is a rate at which work is done, the power is also 0. So it's very important, guys, that you guys read properly through your problems and you answer them according to what you know as being your definition for each and every problem. Okay, this is grade 12. It can get tricky, so it's important for you guys to make sure that you read each and every detail of what is happening. Okay, so number 4, it says when doing a chin up, a physics student lifts her 40-kilogram body at a distance of 0.25 meters in 2 seconds. What is the power delivered by the student? So basic student's biceps. So here, basically, you do have your mass. You can calculate your force. You can calculate your force using the 40 kilogram. You have your distance here, and you've got your time. So let's see how this was done. So the work done by the biceps is a non-conservative force, and that is obviously what the gravitational potential energy Yes, it has to be gravitational potential energy because it's a person lifting her body. Okay, so increase the net of mechanical energy of the system. Okay, the work done by the bicep increase the net mechanical energy of the system. So the kinetic energy is zero because obviously she's not moving around. They're just lifting something up, doing a chin up exercise. Okay, so the kinetic energy is zero, and at the top and bottom, so we are only interested in the gravitational potential energy. So for us to find the potential energy, it's going to be mgh, which is equals to, because we're working with a change in potential energy, it's going to be hf minus hi, and already that's a difference, remember, because it says the distance of 0.25, so that's a change in distance. And we've got our gravity, which is 9.8, and we've got our mass, which is 40 kilogram. Okay, so our non-conservative force, work done, is going to be 98 joules. So once we have the work done, now we can calculate the power, which is work divided by time. In this case, we were given 2 seconds, and that is going to be 49 watt. Okay, are we good? Are we together? I'm glad. So now we continue. So on number 6, it says an escalator is used to move 20 passengers every minute from the first floor of a shopping mall to the second. Okay, you guys understand that? An escalator moves 20 passengers every second from first floor of a shopping mall to the second floor. The second floor is located 5 meters above the first floor. The average passenger's mass is 70 kilograms. Determine the power requirement of the escalator in order to move this number of passengers in this amount of time. Okay, so what we need to know is that the work done will be to move the total mass of 20 passengers vertically 5 meters. Okay, so what do we know about vertically? Vertically is usually us dealing with gravitational potential energy once again. So this is the gravity. So we are not given the mass of the elevator itself, so we assume that we can ignore it, but the total mass will be mass is equals to the number of people and the number of the mass per person. Okay, and that's going to be 1,400 kilograms, because they said it moves 20 passengers, and they said the average passenger's mass is 70. So the total mass for the number of people that the lift should be able to take is 1,400. So now we need to know how much work done is required um, from the elevator to carry these people, and then the work done is going to be mass times gravity times height. So the height is 5 meters upright, so this is going to give us 68,600 joules. Okay, from there, which means this is how much you need. This is the requirement, the work done requirement of the escalator for it to move this number of people. But now we need to know the amount, when you put the amount of time, what is the power that is also required. So the power is going to be work divided by time, and that is going to give you 68,600 divided by 60. And the answer there is going to be 1,143.33 watt. Okay, I hope that we're still together. So basically here, we worked to the requirement because we were not given how much the escalator is, but it's not what was important in this case. What was important was us to know what is the requirement, basically, the power requirement of this escalator. Okay, so I hope that you guys got this right according to the homework that you were supposed to do. Then now we move on. Okay, so today we're going to be doing revision for work, energy, and power. So there is some work that we're going to be doing here, but we're going to be working quite closely. So basically, we're going to be working mostly in the textbook, doing revision. So we're going to be, there's a page in Siavula textbook, page 157, and the study and master as well. We're going to be doing some problems there. And I hope that you guys are ready for that. It's a revision work, and I hope that you know all about your work, energy, and power. Okay. Okay, so these are the quantity and symbols that we work with in this chapter. We've worked with on work, energy, and power. We've worked with velocity for looking for the kinetic energy or for even power, because remember, power is force times velocity. Okay, and we've worked with energy. We've worked with work done, kinetic energy, potential energy, mechanical energy, and power. So these are the symbols that we've been working with in this chapter, and I hope that you guys are keeping them in mind. Okay. So with energy, it's always Newton per meter or kilogram per meter square S minus 2 or joules. Okay. So these are the ones that you need to know. And here, still this one have direction. So which means these ones are vectors and these ones are scalars. They do not have direction, okay? And then these are some of the formulas that we've worked with in this chapter. So for work done, we always know that it's force times distance times the angle, okay, of inclination or no inclination. If there's no inclination, you can just say cos 0, it's going to just be 1. If it's moving in the opposite direction, it's going to be cos 180 degrees. If you're moving forward or whatever angle, if it's 30, then you can plot your 30 there on your cos angle, okay? So that's basically the work done. That's a formula, that's a standard formula of the normal work done on a object, okay? And then we also have the kinetic energy, okay? Tend to be asked, this is the kinetic energy, is the energy, is a motion energy basically, something that is moving, you know. It's usually a kinetic energy, kinetic force. So that as well, this is the formula. This is the formula that we use for kinetic energy, okay? So the kinetic energy of an object is the energy that it possesses due to its motion. So if it's moving, it will have kinetic energy, but when it stops, its kinetic energy will be equals to 0. Okay? Then what we also have is our potential energy. So this one is the energy possessed by a body by virtue of its position relative to other stresses itself, etc. Okay? So potential energy, it's basically, it's got to do with gravitational potential. Okay? It's a force due to gravity. So that's why we also have gravity in our equation when we calculate the potential energy. Okay. So then you also have what we call power. Power is the rate at which work is done. Okay. And you can even see that. You can even see that in the formula because it's work done divided by triangle T. So this is the only thing that's added. It's the time, that with respect to time, once the work is done with respect to time, then now we have power. But you can also say power is equals to force times velocity. Okay, so these are our power formulas that we've used in this chapter. Then we also have the net work done, which is equals to the change in kinetic energy. Okay, it's equals to the change in kinetic energy. So other work done that we've done is work conservative. The work conservative, you know, it's usually one that is gravitational whenever there's frictionless bodies, or, you know, no resistance to the movement, etc. Then we have the change in potential, negative change in potential energy. So this is what we get. This is our formula for work conservative. And then work non-conservative, that's the one where we'll have the change in kinetic energy plus the change in potential energy. So this is work non-conservative. Check how they differ. It differs from the net work. The net work is going to be the change in kinetic energy, and the work non-conservative is the change in kinetic energy plus the change in potential energy. So work done. Okay, work done is a force. When we talk about work done and there's a force at an angle, basically this is what we mean. If you guys remember, we've done problems where they say an object is being pulled at an angle. Okay, work is being pulled at an angle. So this is what we have. So this will be our object, and there you are, busy trying to pull the object in this direction. Okay, so you see that this is in an angle. So why do we use F cos theta? We use F cos theta because the one of the definition of work done is that it needs to be, work will be done if the force is parallel to the displacement at which the object is moving on. Okay, so in order for us to get, you see here, this F is not parallel to the D. So for us to find a length that is parallel to the D, we need to use the component of the force. So here vertically you would have F sine theta. So here you have F cos theta. So this F cos theta is the component that is parallel to the displacement, which is what we have here. Okay, I hope this picture makes a bit more sense to you guys. Okay, then moving on. Now we need to, I wanted to just, you know, go back to checking if you guys got it right when it comes to the positive and negative work. The direction of the force compared to that of the displacement determines if energy is added or subtracted from a system. Okay, so I hope that you understand what that means. So basically what it means is that when force and distance is moving in the same direction, our work done will be just positive. Okay, and the cost will be zero because it's not at an angle. It's literally parallel to the displacement. Okay, so which means in this case maximum energy is added. Okay, guys, these are important stuff that you guys need to know as grade 12 students. They could ask you even in a multiple choice, if if and give you a problem like this and ask if the work done there is the cost is equal to zero, what is energy added or subtracted in the system. So those are certain things that you guys need to know as well. So this is what they give you here. It says work done is FD cos zero, which means the maximum energy is added into the system. Okay, and then we move to this one. So this one looks very similar to this one that I was talking about here, where they pulling. Remember, I told you guys before that when you pull something, which means that it's a positive thing because um, the distance and the force is moving in one direction. Okay, so this one will be cos theta. So depending on what your sign is, because this one is at an angle, so we need the component that is parallel to the displacement that we have there. Okay, so it says less than maximum energy added. So there will be energy that's added, but not maximum energy. Okay, then we move on to the right angle triangle. Okay, in this case, in this case, what you see that's going on here is that the distance and the force are perpendicular to each other. So if these things are perpendicular like this, it means that there is no work done, honestly. There is no work done. So zero energy is added into this system because you do not have anything that you can calculate your work done with because um, this force is perpendicular. Okay? And then moving to the next one, we'll go to this one right here, where the distance is moving this way and the force is opposing. Okay, so this one, it means that maybe um, it's pushing. Yeah. So basically, if the force is moving on that side, it means that it will be at cos theta, but your component will be facing the opposite direction from your distance. So what does that mean? If it's pointing in the opposite direction, it means that it's 180 degrees out of, no, this one is not, this one is just facing the opposite direction, which will mean that it's going to be a negative, okay? And when it becomes a negative, it means that less energy is going to be subtracted in the system. Okay, so energy is subtracted in a system because it's moving in the opposite direction from the displacement. Okay, then we move on to the last one, which is this one right here. Here is basically when the force is not inclined but moving in a totally opposite direction. So this one, it's going to be, it's going to be 180 degrees out of phase. Okay, so if something's 180 degrees out of phase, it means they are both on opposite sides. Okay, so which means the maximum energy is subtracted from this system. Okay, I hope this is giving you a clear picture of understanding. So now let's start with our revision questions. Okay, it says here, how much does a person do in pushing a shopping trolley with a force of 200 Newton over a distance of 80 meter in the direction of the force? Okay, so if they're asking for the work done, it's going to be F triangle X cos theta. But what you see here, as much as, remember I said when I say it's pushing, it's usually repelling. No, this one, it's pushing, but it's pushing in the direction of the force. Okay, so the force and the shopping trolley, they both moving in the same direction. So this is what you will get when you do your calculation. Okay, so your answer is going to be 16,000. Okay, so now we move on. It says here, how much work does the force of gravity do in pulling a 20 kilogram box down a 45 degrees frictionless inclined plane length of 18 meters? Okay, so here they might have said quite a lot of things. They might say a lot of things, but what is most important is that we know that this is a conservative work done conservative. So here it's going to be just the normal force. Okay, and it's going to be the component of the gravitational force parallel to the slope, for example, in line with the direction of the displacement. So FGX is going to be FGX sine theta is equals to mg sine theta of the slope. So the work done can be calculated, which will be mg sine theta slope over triangle distance times cos theta. And that will give you 2,494.67 joules. Okay? Hope that we are good to go. Okay? So now I'd like us to go and check some more problems. I'm just trying to think, where can we look for our problems? Let's try the study and master textbooks. These ones that I just did now, I got them from the Siyavula textbook. So let's do this summative assessment. Guys, I'd like you guys to really attempt these summative assessments because I want us to work with them. I'm sure by now you understand most of the stuff that is happening here in this classroom or in this chapter that you've been doing, which is mechanics unit 3. So I'd like us to work through these summative assessment. So here they ask, give one word for each of the following description. Okay, so this they say the product of force, the product of the force applied and the displacement brought about by this force. What is it called? Okay, is it A, the product? Is it, oh, they said we must give one word. This is the work done, guys. Do you guys see it? Yes, this is a work done, basically, because remember it's a product of distance and force put together. So this is the work done. Okay, so on number 2, it says the energy that an object has that depends on the speed of the object. Okay, remember what we spoke about. I think this is kinetic energy. Remember, we spoke about that kinetic energy is the energy that an object has due to its motion. So this is the same one. It is the kinetic energy. Okay. So number C, it says the type of force that does work on an object, which is dependent only on the initial and final position. That is obvious. We've worked with this definition before. This is the conservative force. Remember that lady going up the steps, the picture that we once had of a lady going up the stairs and down the stairs, and they mentioned that it doesn't matter. It just depends on y0, y initial, y final, y final, y initial. That's the only thing that's important. And that is conservative force. Okay. So moving to C, it says the type of force that does work on an object, which is dependent only on the initial and final position. Okay, that one we did. Number D, it says a quantity that is equals to the change in kinetic energy of an object. This one is so easy, guys. This is the network. Remember, the network is equals to triangle EK, kinetic energy, okay? And then number E, it says the rate at which work is done, okay? This one is obvious. We've just been working with that right now. That is indeed power, okay? So the number 2, they say, correct the following statements. No work is done by force that lifts a mass upwards. Okay? So what is the correct statement? The correct statement says work is done by the applied force when a mass is lifted upwards. So there is work done by the force that is lifted upwards. Okay? So B, it says a non-conservative force does no work on the body if the body is moved around a closed path of this force. Okay? So here, when you correct that statement, it says, when a force does work on an object that moves at a constant velocity, the power due to the applied force is given by force times velocity. Okay? Okay. No, so this for this one, where it says a non-conservative force does no work on a body that is moved in a closed path of this force. No, here actually it's a conservative force does no work. Remember, a conservative force only deals with point A to point B, point B to point A. Okay? It doesn't deal with a pathway, basically A to B. So this is a conservative force does no work on a body if the body is moved around in a closed pathway. Okay? So number C says, when a force does work on an object that moves at a constant velocity, the power due to the applied force is zero. When a force does work on an object that moves at a constant velocity, the power due to the applied force is zero. So the correct answer is, when a force does work on an object that moves at a constant velocity, the power due to the applied force is given by force is power is equals to force times velocity. You guys remember we did that earlier yesterday when we were doing power. So this one is different. When a body is moving at a constant velocity, the power will be force times velocity. Okay? So for mechanical energy is not conserved in a swinging pendulum because the tension in the string does work on the pendulum bob. So the correct answer in this case is mechanical energy is conserved in a swinging pendulum because the tension in the string does no work on the pendulum bob. Okay? Okay, let's do just one last one, and then we're gonna move. We'll do some of the stuff for homework and continue with this summative assessment tomorrow. Okay. So it says here, two people will always have the same power output when they run down a flight of stairs in equal time. Okay. So no, this statement actually should be two people who only have the same power output when they run down a flight of stairs in equal times if their masses are the same. Okay? I hope we are good to go because that's what I had for us for today. This is our exercise that we did in class. But nonetheless, you guys can do self-study and please let me know if you do have any other problems. So this is what I'd like us to continue from number 3 tomorrow. But if you do have study and master textbook, please try and get it. Please try and do some of these problems. These problems are really gonna. We need to close it with a bang. Okay. Thank you guys so much. I think for now we have reached the end of our class. Okay. So thank you guys so much for joining me today for Physical Sciences Grade 12. If you have any questions whatsoever, contact me on t32tndlovu@gmail.com and I'll be able to address any problems that you guys can encounter with regards to physical sciences and mechanics part 3. Okay. Thank you guys for your time and I'll see you guys tomorrow, same time, same place at 9 o'clock. It's the STEM Digital School. And thank you and goodbye.